Welcome. So, if you've ever cracked open a serious physics problem book, you've definitely come across the name Irodov. His problems are legendary, right? They're tough, for sure, but they're also designed to give you this really deep, intuitive feel for physics. Today, we're going to tackle one of his classics, one that looks pretty scary at first, but is actually a beautiful example of just applying the core rules. So here it is. We've got this chain just kind of draped over a smooth sphere. We let it go, and boom, it starts to slide. Our job is to figure out its acceleration. Now, when you first look at this, you're probably thinking, okay, wait, every single link in that chain is at a different angle, which means gravity is pulling on it differently. How in the world do I deal with that? And you'd be right, it's definitely not as simple as a block sliding down a ramp. But that's exactly what makes this such a great problem to solve together. Look, the trick to any problem like this isn't trying to see the entire solution in your head all at once. It's about trusting the process. We're going to build this thing up, piece by logical piece, and I promise you, by the time we're done, it's all going to click into place. You've got this. All right, here's our game plan. We'll start by opening up our toolkit to make sure we have the right fundamental law. Then we'll map out our strategy, our plan of attack. Once we know what we're doing, we'll jump into the execution. That's where we'll do the math. And then, maybe the most important part, we'll get to the insight, where we step back and ask, does our answer actually make any sense in the real world? First things first. Before we write a single equation, we have to ask ourselves, what's the fundamental physics principle that's running the whole show here? Picking the right tool is half the job. And there it is. Good old Newton's second law, F equals ma. It's pretty much the bedrock of all classical mechanics. It tells us that the total force pushing or pulling the chain is going to be equal to the total mass of that chain times its acceleration. It's simple, it's powerful, and it is exactly the tool we need. Okay, but here's the real puzzle, isn't it? If this were just one little block, F equals ma would be easy. But with the chain, the F part is complicated. Gravity is pulling down on every single link, but the direction of the sliding force is different for each one. So how do we calculate the total force that's actually making it move? And here's the secret weapon that physicists use all the time. Instead of trying to wrestle with the whole chain at once, we're going to zoom in, way in, on just one tiny, microscopic piece of it. We'll figure out the force on that one little element. Then, we use the power of calculus, specifically integration, to add up all those little forces from all the little pieces. It's the ultimate divide-and-conquer strategy. All right, we've got our core principle and our secret weapon technique. Let's lay out our exact step-by-step battle plan. It's a simple four-step recipe. 1, we'll define a tiny piece of the chain. 2, we'll figure out the forces on just that one piece. 3, we'll use our calculus trick to add up the driving force for the whole chain. And 4, we plug that total force into F equals ma. If we just follow these steps, they'll lead us straight to the answer. Okay, this is where the fun begins. It's time to see how this elegant plan actually works with numbers and symbols. Let's get our hands dirty. First up, step 1, we need to pick our tiny element. So let's imagine a little segment of the chain, and we'll call its mass dm. It's located at some angle theta, down from the very top of the sphere. And this tiny little piece has a tiny little length that we'll call ds. So how much mass is in this little dm? For that, we use a concept called linear mass density, which we represent with the Greek letter lambda. It's just a fancy way of saying mass per unit of length. So the mass of our tiny piece is simply its tiny length, ds, multiplied by this density, lambda. This is the key that connects the chain's shape to its mass. Step 2. What are the forces acting on our little piece? Well, the problem says the sphere is smooth, so we get to ignore friction. Phew. The main player here is gravity, which always pulls straight down. But, and this is crucial, the chain can't just fall straight down. It's stuck on the surface of the sphere. This means we have to break the gravity force into two parts, or components. There's a part that pushes into the sphere, the normal component, but the sphere just pushes right back, so that's a wash. The interesting part is the component that acts along the surface, tangent to it. A little bit of trig shows us that this force is dmg times the sine of theta. This is the force that's actually making the chain accelerate and slide. Okay, everybody pause for a second. This is a super common trap, so I really want you to hear this. It is so tempting to look at that force dmg sine theta and just set it equal to dm times w, but you can't do that. Why? Because that acceleration w belongs to the entire chain. Every link moves together. You can't equate the force on one tiny piece to the motion of the whole thing. We have to find the total force first. So to do it the right way, we move to step 3. We need to find that total force. And we do that by summing up or integrating all those tiny little tangential forces, DFT, for every single piece of the chain from the top all the way to the bottom end. Let's build this integral. We know dm is lambda times ds. And from basic geometry, we know that a tiny arc length ds is just the radius r times the tiny angle it covers, d theta. So we substitute that in. Now what are our limits? We're summing from the very top of the sphere, where the angle theta is 0, all the way to the end of the chain, which is at an angle of L divided by R. And there it is. Our integral is all set up. And now we just have to solve it. The integral of sine is negative cosine. We evaluate that at our two limits, do a little bit of algebra, and what we're left with is this nice, clean expression for the total driving force on the entire chain. We are so close. We're on the home stretch now. Step 4 is to bring it all back to F equals ma. We have our total force, F, and the total mass, m, is just the density, lambda, times the total length, L. So we set our force equal to lambda L times the acceleration w we've been looking for this whole time. From here, it's just a little bit of rearranging to solve for w. And notice something really cool here. The linear mass density, lambda, is on both sides of the equation, so it just cancels out. That tells us something physical. The acceleration doesn't actually depend on how heavy the chain is, just on its length and the sphere's radius. And there it is, our final answer. Okay, we've got a formula, we've got an answer. But in physics, we're not done yet. The last and maybe the most important step is to lean back and ask ourselves, does this pile of symbols actually make any sense? A great way to do this is with something called a sanity check. Let's think about an extreme case. What if the chain was really, really short, almost 0 length? Just think about it physically. A tiny little chain balanced right at the very top of the sphere. It should barely move, right? Its acceleration should be pretty much 0. The question is, does our fancy formula agree with our gut feeling? And what do you know? It absolutely does. There's a handy math trick for when an angle is very small. And when you apply it here, it shows that as the length L gets smaller and smaller, the acceleration W from our formula also gets closer and closer to 0. The math perfectly matches our physical intuition. That's when you can feel really confident that you've got the right answer. You see, the real lesson here isn't just the answer to this one problem, it's the method. This technique, breaking a big, continuous thing into tiny little pieces, analyzing one piece, and then using calculus to sum it all up, is one of the most powerful tools you'll ever learn in physics or engineering. So think about it. Where else could you use this? Thanks for working through this one with me.